Okay, so now in this thermodynamics, we are going to look at energy. So energy is the ability to do work, or in the other way, we can define energy as the ability to transfer heat. So what is work? A work is an energy that you use to cause an object that has mass to move. So remember from basic physics, work is force times distance. So if you have energy, if energy is used to cause an object to move, so that kind of energy is known as work. And we have heat. Heat is also energy that used to cause the temperature of an object to rise. So what are the unit of energy? The SI unit of energy is joule. So 1 joule is something as kilogram meter square per second square. So the other way of representing the SI unit of energy, you can use kilogram meter square per second square. And all the non-SI units is still in a widespread use. So the calorie. So we also have, at least from here, we can see that we have like 3 different units of energy. We have joule, we have kilogram meter square per second square, and we have calorie. And we should know that 1 calorie is something as 4.184 joule. So in the course of this course, you will see that we'll be using any of the, especially joule and the calorie. And also the SI unit, or energy has an SI unit of, or a formula of mass times velocity square. And remember that kinetic energy is always have mv square. And then the work, so energy used to move an object over some distance. So that is why we have work is equal to force times distance, where W stands for work, L force, D distance. Not that units, that force is equal to mass times acceleration, and then work is equal to force times distance. So therefore we have mass times distance square all over or per second square. Then we have mv square, because distance square all over second square stand for velocity. So therefore work can be mass times velocity square. So heat is a form of energy that also be transferred as heat, and heat flow from warmer object to cooler object. So generally we have a heat flow from a cooler object to hot object, so that to maintain the equilibrium balance. And we have kinetic energy. Kinetic energy is the energy possessed by virtue of its motion. So when we have the motion of an object, well, the object is moving, or is changing position from one point to another. So that type of energy is called kinetic energy. So kinetic energy is half mv square. Then we have potential energy, is the energy due to position or a chemical composition. So when we have an object at rest, look at it. This is a rider riding a bicycle, and you see that at this point it is at one position, it does not move. So the potential energy here is higher, while here, as the object is moving down or is going down, then the potential energy is less. Then transferal of energy. Add potential energy to a ball by lifting it to the top of the wall. So look at it. The potential energy, this is the height of the ball, and it is at the top of the wall. And here we see that as the volt falls. So you see the volts now falls. So therefore it is covering a particular movement. So therefore the potential energy is now converted to kinetic energy. And now the ball hits ground. So since the ball hits ground, kinetic energy is now zero since it stopped moving. But E, which is the energy, has to go somewhere. So balls get squashed, then heat becomes zero. So energy accounting, we must identify where energy or where different types of energy go. Therefore, we must identify the places. So I explained system and surrounding on the other videos. So now the next thing that we are going to look at is the first law of thermodynamics. So the first law of thermodynamics said that the energy conserved, meaning that during a chemical or physical process, energy can neither be created nor destroyed, but rather can be transformed from one form to another by transferring it between a system and the surroundings. So one very important thing that we need to understand under this first law of thermodynamics is that the energy can neither be created nor destroyed, but it can change from one form to another. Let's now give example. We have chemical energy. So chemical energy is usually stored in the food that we are taking. So if we now take a food, the food will now be digested. After the digestion, then it will now undergo some metabolic process, and at the end, the energy in the food will be harnessed in the form of ATP. That ATP will now be hydrolyzed to give or will now be hydrolyzed for mechanical work. So it means that the energy is now stored in food in the form of chemical energy is now converted into ATP. So now the ATP will now be hydrolyzed, which is used in the mechanical work. So meaning that it changed from chemical energy to mechanical energy whenever there is a mechanical work. And as a result, or after the mechanical work, the ATP hydrolyzed will now produce or will now change the energy from that mechanical energy into another form of energy known as heat. So with this, we need to understand that in the other way of defining this thermodynamics or the first law of thermodynamics, it means that the total energy of the universe is constant, meaning that energy can neither be created nor destroyed in the universe, but it can change from one form to another. Typical example, the energy in a solar energy is converted into mechanical energy. That is, the energy from sunlight will now undergo photosynthesis to produce ATP, to produce food, and the food is now actually have its energy in form of the chemical energy, and the chemical energy will now be converted into mechanical energy when there is after the digestion and the body, the ATP will be produced, and as a result of mechanical work, it will now be hydrolyzed. Then the energy produced as a result of hydrolysis of ATP due to mechanical work will now be converted into heat, and the heat energy will be released from the body system to the surrounding, that is to the environment, and in the environment, the heat energy will now be used to convert into another form of energy. So it's a cyclical process. The first law of thermodynamics is just trying to give us an idea of how energy is conserved from one point, or is conserved, and it can just only change from one point to another. And one thing that I want us to understand here, we have a formula, and the formula said the energy of the universe is equal to the change of energy in the system plus the change of energy in the surrounding. So since we know that the energy is constant according to the first law of thermodynamics, so therefore the energy of the universe is now equals to zero. So as a result of that, the formula will now change to change of energy in the system is equal to minus change of energy outside the system, that is at the surrounding. So now This is a typical graphical demonstration of how this internal energy is. Look at it. This is the initial state and this is the final state. So at the initial state and the final state, this is the energy at the initial state and this is the energy at the final state. So we can now see that the energy at the initial state is less than the energy at the final state. So therefore the change of energy is is negative. So therefore energy is lost to the surroundings. Since the change of internal energy here, as we have, the final internal energy is less than the internal energy. So therefore now, since the final internal energy is this, so therefore the change in internal energy is less than zero. So since it is less than zero, it means that it is negative. And remember, this change in internal energy is also similar to the enthalpy changes, or the change in enthalpy. So the change in enthalpy is equal to the change in internal energy. So therefore, the change in internal energy here is negative. This implies that the process is said to be exothermic. Then the next one is the final energy is greater than the initial energy. So therefore, the energy is gained from the system to the surrounding. Therefore, the process is said to be endothermic reaction. So now the next thing that we are going to look at is the internal energy. So the internal energy of the system is the sum of all the kinetic energy, potential energy of all the components of the system. So we call it internal energy. So the change of internal energy is the sum of the energy that are in the system. And this sum of the energy, we have potential energy, we have kinetic energy, we have the energy of electrons, we have energy of the nuclei, then etc. So almost impossible to calculate the total internal energy. Instead, we always look at the change in the internal energy. So it's very, very difficult to calculate the total internal energy. So the simplest way is to calculate the change in that internal energy. And one thing that I wanted us to understand here is the first law of thermodynamics, we said that the internal energy of the isolated system is constant. So it is usually expressed using a formula, and we will talk about the formula next. Okay, so now look at the change in internal energy. So to calculate the change in internal energy is the same thing to set the final energy minus the initial internal energy, and at the end from here we'll be able to derive whether the change in internal energy is negative or positive. So if it is negative, it's exothermic, and if it is positive, it's endothermic. There is a change in internal energy. If delta G is greater than zero, that is the final internal energy is greater than the initial internal energy. Therefore, the system absorbs energy from the surroundings. This energy change is called endergonic. Okay, ladies and gentlemen, I think I have to explain something here very important. You see here we said endergonic. And the other one we said endothermic, because the other one is called exothermic and exothermic because we are dealing with heat. That is why it's thermic. But this one is internal energy. We are talking about the energy itself. So therefore, we no longer call it endothermic, but rather endergonic. And then the next one is the when if delta E, or the change in internal energy, is less than zero, meaning that the final internal energy is less than the initial internal energy, and therefore the system will release energy to the surroundings. And this one is said to be exergonic, since the change in internal energy is negative. And then the next thing is the changes in internal energy. So when internal energy is exchanged between the system and the surrounding, it is exchanged as either heat, Q, or work. That is, so the change in internal energy is equal to Q plus W. In other textbooks, this change of internal energy or delta E can be used or can be represented with delta U. And one thing that I wanted us to understand is because this change in internal energy or the first law of thermodynamics is usually operated under isolated system. So if it is under isolated system, the change in internal energy is now changed from delta E plus or yes delta E plus Q plus W. So for an isolated system, both Q and W are equals to 0. So delta E for the system is 0. So therefore, if the system where there is actually when the system is isolated system where internal energy is operating, so Q, that is heat, and the work are usually 0 because there is no exchange of mass and energy between the system and the surrounding. So therefore, the work done and the heat is equals to 0. Therefore, our change in internal energy will also be equals to 0. And then for and then the system gains as heat, that's plus Q, and loses as internal energy. So the first law could be stated that in a closed system. So if it is in a closed system, the change in internal energy is equal to the differences between heat absorbed by the system and the work done by the system. That is delta U is equal to Q minus W. So I think we need to understand here. It's very, very important for we to know which types of the system we have when we are trying to talk about this first law of thermodynamics. If it is closed system, or let me start with an open system. So if it is open system, Q is equal to 0 and W also is equal to 0. Therefore, delta E, the change in internal energy, is now equals to 0. That is if the system is isolated. If the system is isolated. But in a situation where we have closed system, then the change in internal energy will now change to something like this. The change in internal energy, that is delta E, is now equals to Q minus W if the system is a closed system. So we need to understand this. And then the thermodynamic law of thermodynamics could also be stated as follows. It is possible to create a perpetual motion machine, that is a machine that does not work without a fuel or some other source of energy. So I think from this, we are going to, after actually these slides, we are also going to look at some other, or we are going to look at some calculation. Okay. So now, after this, we have for Q, it means if the Q is positive, means the system gain heat. And for W, if W is positive, mean the work done is on the system. And for if delta E is plus, means net gain of energy by the system. And if they are negative, that is, if Q is negative, means the system lose heat. And if W is negative, means work done by the system. So, and if we have delta E negative, means there is a net loss of energy by the system. So we need to understand whether the system get energy or the system lose energy. So when delta E is positive, it means that the system gain energy. That is then, and if it is negative, it means that it's the system that lost energy. And if W is positive, it means that it is work done on the system. And if it is negative, it means it's work done by the system. And if Q is positive, means the system gains heat. And if it is negative, it means that the system lose heat. So now look at these examples here. We see that we have surroundings suck heat out of water. So this is the surrounding. So it's suck heat out of the system. So yes, to the surrounding. That is from the system to the surrounding. So that is why it means that the heat is lost from this container as a system outside the surrounding, because the hot water is trying to cool. So as a result of this, it means that delta E the Q is negative because the heat is losing. We are losing heat. And look at this one, it is positive because this one is the ice water, and Q is positive, meaning that the system is absorbing heat. So it means that the Q here will be positive because the system here is gaining heat. Okay, I think for this, I'm going to stop here.